We can start. So before we do you have any questions on project? Again, it's easy, but it might be the first time you're seeing this sort of stuff, so it might take some time. No? All right. If you do, email me again. We can set up. If you're distance learning, we can set up a Skype meeting and go through your steps. So we were talking about advection, right? Up until now, we've been talking about the heat equation and advection, and we've seen that how all of this sort of combines into this big Navier-Stokes equation, the conservation of momentum. And we will use each individual piece that we have been learning in solving the full equation. But before we get there, we'll start with that next week. There are some loose ends to tie up. Again, just a few important things to know that will help you solve not just these PDEs, but it's helpful for general computation. Okay, so yeah, today I will finish up with characteristics that we were talking about last time. The characteristics, how they're related to the behavior of the PDE. Then we'll look at some more code examples of how to do large matrix computations very, very efficiently. Okay, so if you remember, our advection equation is for a passive scalar, it's del phi by del t plus u del phi by del x equals 0. And this has an analytical solution. And we were looking at numerical results. But analytically, you can say phi at any, not x, phi at any x comma t is actually the initial shape, phi naught, just advected with velocity, let's say ut. Okay, I've used u here. I might have used c in the previous class. Okay, and we looked at what that looks in terms of a numerical solution. Right. I had this initial Gaussian pulse, and then I was solving the advection equation, and it basically advects. Okay. This looks like a very, very simple thing, very intuitive thing, but it's a bit tricky to code. And you will actually get to do this in one of your projects. And you see there's some errors starting to happen here, and as we keep propagating, these errors will keep growing. Okay? That's a given with numerical solutions. We always have to try to minimize these errors in some way. Okay, but now, how is this related to characteristics? If we talk about what happens to the solution, so we have this initial Gaussian pulse, and at, let's say, at time tn, and this goes to, let me see, let's call this x. Okay, let's divide this up. Okay, fine. Okay, let's say our computational domain has these numbers from 1, 2, 3, 4, 5, 6, 7. This is I equal, okay? And this is at time tn. What will happen at the next step is this will move to the right. So let me see. This will go over to here, and I will try to redraw this pulse nicely, but I will see. Okay, and this guy comes over here. Yeah. All right, so what happens here is information or the packet of fluid has moved from this peak to this new peak. Just everything has just shifted to the right. So this is at Tn plus 1. Okay? And the characteristics come into play here. This blob moves over there, that blob moves over there, this blob moves over there. Okay? And all of these lines have the same slope. Slope of these characteristic lines is equal to u. Okay, that's the speed with which my information propagates. And this will keep happening in time. At Tn plus 2, again, you get another shift. So conceptually, this is what characteristic means. They represent the path along which information travels. Okay? And this sort of a diagram is called an XT diagram. This is called an XT diagram. So one thing that's nice with the advection equation is we can assume our u is constant. It's not dependent on space or time. And in that sense, the characteristics are straight lines. But if the u actually is dependent on x, these will become curved lines. Okay. We're not going to go much into a lot of detail about this, but let's just look at the wave equation. So this is the advection equation, and if we look at the wave equation, so this was a solution of the wave equation. You start with an initial pulse. What will happen is it will split up and move to the left and to the right. Okay? So that's the initial condition, and splits up into two pulses, gets reflected at the boundaries, comes back, gets superimposed, and it'll keep going unless there's some sort of dissipation. So what about the characteristics here? Do you have some idea of these are hyperbolic equations, right? Do you remember how many characteristics for hyperbolic equations? Two, yeah. And that's exactly what's happening. There's a left-leaning characteristic and a right-leaning characteristic, and information propagates along these two lines. Okay. So that was the solution for the wave equation. Okay, which is del 2 phi over del t squared equal minus c squared plus c squared. C squared del 2 phi over del x squared. Let me check if it's a plus or minus. It is a plus. Perfect. And again, this inviscid wave equation has an analytical solution called the D'Alembert solution. Okay, which is just phi is a linear combination of these left and right moving waves. So phi of x comma t is just g1, a left moving wave would be x plus or minus plus u c t plus g2 x minus c t. Okay, so that's the two pulses that separated out and were moving towards the left and the right. Okay, now there's something very important that these characteristics tell us. So again, if we draw the XT diagram again, what happens now is, let's see, I will need your help to tell me if, again, there's an X, there's a T, okay? And let's say this is my time of observation. So there's an observer here at T observation. And if I have one point, Okay, I'm interested in one point. What will happen to the information over here? So if I start thinking about what path it follows, and for the wave equation, what's the logical thing that should happen? Is the question clear or not?
It would convect to the right or left, right?
Right or left?
It would be both.
Yeah, it's the wave equation, exactly. So the information would propagate both to the right and to the left, okay? So the characteristic lines look like this. And there's one with a plus c slope and one with a minus c slope. C is, again, velocity, c or u, okay? So it's, in the beginning, it's sometimes a bit confusing about what this xt is. X would just be at time equals 0. I have my profile that looks like, for instance, that's what we were doing here, right? At time equals 0, the profile looks like a Gaussian. At time equals 1, the profile moves to the right. So that's what xt represents. So the information over here moves to the right and to the left. So all of the points in this region are influenced by this point. Okay? So this is called a domain of influence. Okay. What about this region, the other cone? Again, with the same lines. Okay. What's the importance of this region? So we were saying everything at this point affects everything that happens in time later on, okay? But only along within these confines. What about the lower part?
Dependence?
Yeah, this is called the domain of dependence. The reason for that is everything that happens in this region actually influences what happens at this point. Okay? So this is called the domain of dependence. We see, all right, perfect. And again, in the beginning, it's a bit difficult to immediately see what this means. So let's take a point outside the dashed region over here, okay? Will this point influence what happens at this point? Will the circle influence the square? It will not, because, why won't it? So, it's a very simple reason, but you tell me. Why will this circle not influence what happens at this square?
Outside of the domain of influence.
Yeah, it's outside of the domain of influence, but physically, if you think about waves traveling, how can you relate this domain of influence to that? Yeah. It's okay, take a guess.
No information is received.
Yeah, that's going in the right direction. So if, let's say, we do a thought experiment where we drop a ball on the surface of calm water, right at this point, right? The waves will ripple out. So they will travel with this speed plus c. But if I'm over here, at this x and this t, the wave has not reached me yet. Okay. So it's exactly what both of you were saying. That's the physical reason. I'm too far out at this particular time to have seen the information. Okay. If I move further in time, yeah, slowly the information will eventually reach me. Okay. So that's what the xt diagram represents. Conceptually, does it make sense now? Okay. If not, tell me. Yeah.
Can we distinguish G1 and G2 in that domain, or?
G1 and G2 would just be, let me see, where is the So on the actual solution, the G1 and G2 are the pulses that are moving to the left and to the right. Okay? And on the XT diagram, G1 and G2 would be the solutions that propagate along these two straight lines. Okay? So that's basically what the XT diagram represents. Does that answer your question?
No, for example, can I say that that domain of influence is actually the G1 plus G2, right?
Yeah, it's the solution phi of
solution
x
for
comma t. Yeah. And the G2 function specifically moves along this direction, and the G1 moves to the left. Okay. X plus ct goes to the left, x minus ct goes to the right. So yeah, it's a sum, but both the pulses retain their individual shapes, as we saw in the animation. Okay. All right. So let me see, is there something else we need to look at? All right, so domain of dependence again is every x within this region at these time intervals influences what happens, again because information is propagating in towards the dot. Okay. Okay, so this is for the wave equation. What happens for this is for a hyperbolic equation, hyperbolic PDE. What happens with the parabolic PDE? So parabolic would be, we have the heat equation. Del T over del T equal kappa delta 2T over del T squared, x squared. Okay? So this is parabolic. The slope here is actually 0 for the information propagation. So if we draw an XT diagram, what will it look like? Again, we pick a time where our observer is located, and we pick a point. What happens here? So here, the slope of the characteristic was plus c, which was some finite value. And now we're saying the slope of the characteristic is 0.
So going to be straight.
Yeah, it will be straight lines. So it will be this line, right? It's equal 0. So what this is saying is any disturbance that takes place at this dot influences this whole region. Okay? And at the same time, this point is influenced by the region below. So again, this is the domain of dependence. And the one on top is the domain of influence. All right, so let's think in terms of the heat equation. If we take a rod that's lying here from x0 to xl, and we change the temperature at the center by, let's say, 50 degrees, what will happen? What will happen right at the next time? At one step forward. Okay, possible answers are this disturbance will slowly propagate out, it will propagate out instantaneously. Which one is correct?
It'll slowly propagate.
Use it will slowly propagate out because it behaves like a diffusion, right? That's what we have seen. It will slowly propagate out, but the influence of this disturbance can be felt at all x's at the next time step. Okay. So the influence of the disturbance, this is for parabolic, can be felt at all x locations, but it propagates out in the form of a diffusion. In the form, yeah, let's say diffusion. Okay. All right, and last kind of equation that we looked at was elliptic. And we know lambda squared p equal f of x is one possibility. So that's the Laplace equation, the Poisson's equation. What happens now? What happens if I have the Poisson's equations? For instance, the pressure in an incompressible fluid. What happens if I change something at one point in the fluid?
Since there are no characteristic curves, the information will propagate everywhere.
Yeah, so for elliptic PDEs, there are no real characteristic curves. No real characteristics. For elliptic PDEs. So, a disturbance propagates instantaneously. And this is often a very sort of violent propagation. So if you change the pressure in the fluid domain at one point, you will see it disturbs the whole pressure field almost instantaneously. And it takes some time to settle down. Okay? So that's how characteristics are useful in, again, looking at the behavior of the solution for hyperbolic, parabolic, and elliptic PDEs. Any questions up till now? No. All right, so
So for
Yeah.
that one, you don't have a domain of dependence? Influence?
for the elliptic PDE,
Yeah.
yeah, so these are usually equilibrium problems, so there's no time in here. So it's difficult to draw an XT diagram.
Okay.
So this would be a steady state heat equation. Okay. So yeah, there's no XT diagram. At least I cannot think of what would be the best way to draw an XT diagram.
Mm-hmm.
Can we say it's all a domain of influence? Because
The domain of influence?
yes,
elliptic.
for elliptic,
It's
it's not time dependent, right?
Yeah, you're right. It's not time dependent. That's why it's difficult to specify these regions for which you need an X and T.
Yes.
But if you think about it, just logically, the domain of dependence for elliptic PDEs is the whole fluid domain, because anything that happens at any point influences everything else. Make sense? Okay. Anything else? Okay. So as I said earlier, we need to tie up a few loose ends. So the first thing I'll show you is matrix solution. Right? We all know how to solve AX equals B, but we will take a look at how you can speed up those computations by hundreds of times. So let's take a simple example first. So matrix solvers. So there are direct solvers and there are iterative solvers. And when I say matrix solvers, it's any general AX equals B problem. Okay? and the x equals what? Okay, A and B are known. So two of the most popular iterative solvers are conjugate gradient called CEG, and another one is called GMRES, generalized minimal residual. Have you seen these things before? Have you heard of these? All right, one out of several. All right, perfect. So AX equals B crops up all the time in Navier-Stokes, in astronomy, in biology. And the easiest thing to do here is say x equals A inverse B. Okay? But this is a very, very inefficient way of computing the solution. And this can be very problematic if your problem size is very large. A can be 1,000 by 1,000 matrix. And this inverse can take several seconds if you're lucky, if not minutes. So people have worked on these alternative methods called iterative solvers that assume a particular solution for this A inverse B and then iteratively get a better result. Okay? And this is a whole huge field on optimizing linear algebra operations, and we don't need to get into that. So you almost never have to code. We almost never have to implement these linear algebra solvers ourselves. Okay, there are several very high quality, highly optimized libraries. So instead, use numerical libraries. Okay, there's one called PET-C, you might have heard of it. There's another called LinPack. And there are teams of tens of people who have been working on these libraries for several decades to squeeze out every little piece of CPU power that you can. Okay? So yeah, it doesn't make sense for us to go and reinvent. If you would like to know how these things work, I mean, there's very nice, again, Google has very nice resources. But if you're just interested in getting to your solution, you just need to know how to use these things. And MATLAB has already implemented these things in very straightforward functions. So we don't even need to know how PET-C and LinPack work. Okay? So we will take a look at how this conjugate gradient and GMRES can speed up our computations. Any questions? All right. So for that, let us go back to our implicit heat equation. Implicit solution of heat equation. I will put up a homework sometime today or later tomorrow where you have to do an implicit solve of the heat equation from project 1. So it will basically be the same question, but it will let you see how you can take very large time steps with the implicit solver. Okay, so we had again del T by del T equal kappa del 2T over del X squared. All right, and we have our rod. Let's say T of A1. So let's not write out the full thing. Let's just talk in terms of I plus 1, since most of us should be comfortable by now with this notation. Okay, boundary conditions are given. All right, okay. Okay, so what's the implicit discretization of the speed heat? Help me out. Yeah. So the left side remains the same as before. Time derivative is
tin plus 1 minus tin.
tin plus 1 minus tin over delta t. And the right hand side actually changes when we're talking about implicit solver. So it's what?
Kappa into delta x square ti plus 1 n plus 1 minus 2 ti n plus 1 plus
Sorry.
ti.
Yeah, so with the implicit discretization, we just say everything on the right hand side should be at n plus 1 instead of n. And now all of these are unknowns. All the n plus 1s are unknowns. The only known value is the tin. So for this, we will have to solve a matrix equation. Before that, let me just say, simplify this a bit. So this becomes tin plus gamma ti plus 1 n plus 1 minus 2 ti n plus 1 plus ti minus 1. Okay, where gamma is kappa delta t over delta x squared. I haven't done anything. I've just taken the delta t on that side and said gamma is this and rearranged this. Okay. Now this will give us our matrix that we will solve live in MATLAB. So let's see. So if I regroup things, I have ti n plus 1 times 1 plus 2 gamma. Minus gamma. If I make a mistake, please let me know. Okay, all right. So these are the new t's that I need to know, and the way to compute them is we form this huge matrix. On the diagonal, we have 1 plus 2 gamma minus gamma.
Yo, Ryan.
0, 0, 0, 0. So this goes on, and this is called a tri-diagonal matrix. Okay, and over here I have my t's. So ti times that. Actually, this is t2, t3 n plus 1, blah blah blah, ti n plus 1, blah blah blah, and then something on the right side, b2, b3. I'm not writing t2n because there might be boundary conditions that you have to move to the right side.
Could you move the paper?
Once more.
Can you move the
Oh, yeah, yeah. So let me see. Okay, I will wait for a second till you are able to write that down. So the matrix is, again, nothing. I've just rewritten the system of equations in this matrix form. So Ti times 1 plus 2 gamma would be here. 1 plus 2 gamma times Ti. If for I equal 2 gives me this. Why did I not write it down for I equal 1? Because what?
It's a boundary condition.
Yeah, it's a boundary, right? That boundary condition is T is known. I don't need to solve for it. So I start with I equal 2. So this becomes T2, T3 times minus gamma. That's the one over here. Okay. And this is B2 instead of T2n because the known value, the boundary condition, goes on the right hand side. So here, B2 would actually be T2n and plus n gamma times T1. T1 is known as 100 degrees centigrade. This is the boundary condition. Okay. All right. So we have our Ax equals b that we need to solve. We need to solve for x. Solve for x. All right, so let's go to MATLAB and code this up. All right. Okay, so first, let's say gamma equals 0.2 for instance. And my matrix size is 555. So it's easy for us to see what's happening. And the way I can make this tri-diagonal matrix is using this command called diag. Okay. Let me say, so first, diagonal elements are 2 times gamma plus 1. Yeah, 1 plus 2 times gamma, and we have n of them, right? So times 1s of n, comma 1. Okay, so let me just run that to show you what I mean. Okay, so we have all the diagonal elements here. This is just 1 plus 2 gamma. Okay. Now the off diagonal elements are minus gamma times 1, but n minus 1 of them. Okay, so the off diagonal elements are that. All right, fine. Now my matrix A is actually if I say diagonal elements comma 0, this basically gives me a diagonal matrix with the diagonal elements on the diagonal, right? If I say instead A is off diagonal elements, but minus 1, what will happen? Have you seen this diag before? No. It's just an easy way of forming a diagonal matrix. Okay. So if I say this, diag of off diagonal elements minus 1. Minus 1 just means take the diagonal line, but below, right? The first diagonal line below the actual diagonal. If I had said plus 1, it would have been the one above, right? So let's see. Again, the diagonals are 0 and the one above is the numbers we need. Okay? So if we just take the sum of these things, it will give us our A matrix. That's the center is the first one, this is below, and we have one above. Okay, perfect. Let's see. Alright, so is this what we wrote on the paper? This is 1 plus 2 gamma, this is minus gamma. Okay, let's switch and let's make sure this is what we had. Okay, we have 1 plus 2 gamma all along the diagonal, and minus gammas below, and minus gammas on the upper diagonal. Okay. So that's exactly what I wanted to write, to code. Okay. Fine. What is the next step? E is, let's take the random numbers. Random n comma 1. A, B is some vector. And x equals what? What should I write? What is the simplest thing? Yeah.
Inverse of A times B.
Inverse of A times B. Inverse of A times B. Right? And let me time it. Okay. If you remember, tick starts the timer, clock stops. Alright, fine. So let's run it. Demo 1. Okay, so the elapsed time is 0.00865 somewhere. Okay. But this is a very small problem. We have 5 by 5 matrix. What will happen now? Oh, no. Let me comment out the thing so we don't see. Okay. Stop. Okay, so let's see how long it takes. This is a 5,000 by 5,000 matrix. Okay, elapsed time is 4 seconds. Okay. Let me comment this out. All right. What's another faster way of doing this? Not saying A inverse A times B, but something else. Have you seen this operator? A, that, divide, B. So this basically does the same thing, but it does not compute the inverse. Computing an inverse is very expensive mathematically. So MATLAB will know, okay, I don't need to compute the inverse, I can do the solution by Gaussian elimination or some other method. Okay, all right. So already we're better. Instead of 4.5 seconds, we're 1.2 seconds. And you might think, okay, these are seconds. Why do I care? Remember, when you do an implicit solve, your full simulation might involve 2,000 steps. And each step, if it takes 4 seconds, you will wait for a few hours. So we've already managed to drop it down by, okay? Now let's go to these iterative solvers that I mentioned earlier, which were, once more, what?
Like LU.
LU factorization you can do, but that would be similar to what's happening inside MATLAB for this line. It's doing all these decompositions, maybe Koleski decomposition and factorization, and doing smart linear algebra. The iterative solution actually takes an initial assumed solution for x and then keeps updating it iteratively. Okay? And one of the solvers is called conjugate gradient, is PCG, I think, PCG. Can you just make sure I have PCG?
Precondition conjugate.
Yeah, it's the preconditioned conjugate gradient. Okay, so you can say PCG A comma B. Let's see how long this takes. All right, 1.2 seconds became 0.25 seconds. Okay. Another iterative method is GMRes. GMRes A comma B. Let's see how long this one takes. This should take maybe roughly the same time. Oh, okay, yeah, 0.24 seconds. Okay. So these iterative solvers are much faster when you're dealing with very large matrices. They might not work very well if you're dealing with a small matrix. So if we go back to saying, let's have a 3 by 3 matrix, which we can do on paper, the direct solve will be very, very fast. Let me save this as full time. Okay, I'm just saving the time for each operation. And I did not pre-allocate it, but this is a small thing, so at the moment, I'm fine. Let me think. I think there was one more method I wanted to show you. Let me just make sure. 1, 2, 3, 4. No method. Okay. So if we have a 3 by 3 matrix, just to make sure that you believe that these things are actually solving A inverse B. So that's where's the first solution? Okay, let me comment out okay. So that first x comes from A inverse B. The second x comes from A slash B. Okay, both are the same. This one comes from the conjugate gradient. It's the same number as this, okay, same solution. This result comes from the GM res solution. Again, so we're just making sure they're all solving the same thing. Okay? And for a small system, you will see direct solve is 0, 0, 0, 6. The iterative solves are larger. Okay? But for a large system, that was not the case. If I put it back to 5,000 by 5,000, we will see the iterative methods are much faster. Okay, so full time, all right? Inverse took 5 seconds, A slash B took 1.2, the iterative solvers 0.25. So that's a speed up of, let's say, 4.88 divided by 0.25. That's a speed up of 20 times. Okay. So you will get your solution in 1 hour instead of 1 day, 20 hours. Okay. Again, very simple things which will help you for not just for CFD, but for any sort of computation you do. Python, I'm sure, has the same things. I'm familiar with MATLAB, that's why I'm showing you these in math. Okay, so that's speeding up computation. Now there's something else that we can do. Okay, if we go back and look at our matrix, if this is a 1,000 by 1,000 matrix, how many elements are actually useful in here? Do I need all the 1 million numbers inside the matrix? You're shaking your head, why?
3,000.
There are zeros alone.
There are zeros all over the place. Only the main diagonal and the lower diagonal and the upper diagonal are non-zeros. So instead of saving these 1 million individual numbers, 1,000 by 1,000 numbers in my RAM, why not do something smarter? Have you heard of sparse matrices? No? So this is actually called a sparse matrix. The reason for that is almost every number is 0 except for a very few handful of numbers. Okay? So let me write that down. They're called sparse matrices. Okay? Very few non-zero elements. And there are special ways of storing, special storage structure can save us a lot of RAM. And if you remember from a few classes ago, RAM is a very precious thing in computation today. CPU has, the clock speed has increased significantly, but RAM increases very, very slowly. So anything we can do to save RAM is a huge advantage for us. Okay, so again, most computational software has these things built in. MATLAB has something called SP-diags, which gives you sparse matrices. Python also has SP-diags. C++, Fortran, I don't remember. But if you use those, we can look it up. Okay, so let's take a look at what SP-diags does. So MATLAB, this is called SP-diags. Basically, it's sparse diagonal matrices. Okay. Okay, so that's why I saved this as full time. So these are full matrices. The A is full, not sparse. So let me see, this is full matrices. I will do the same exact thing for sparse matrices. Sparse. Okay, but now I have to create something called a sparse A. And again, we use a command similar to the diax. Let me see, it will be slightly different. Let's see, diagonal elements are that fine. The off diagonals also have to be n, and sparse A is SP diax off. Let me see if I remember. Yeah. So it will be off diagonal. I don't want that. So. Okay. So these are the three vectors that will go at index -1, 0, 1. Okay. Make sense? This again, the main diagonal will get diagonal elements, the lower will get off diagonal, upper will get off diagonal. Am I missing something? Let me make sure. Oh, I have to say, what's the size? It's n by n. So for us, n by n. All right, perfect. Let me do this for the small n first, n equal 5. Just to see what things look like. So now, sparse A does not look like a matrix at all. It's basically MATLAB storing these elements in as linear indices. But if we do full sparse A, it will actually give us the full matrix. Okay. All right. So let's use this sparse A to solve our AX equals B and see. Before that, let's take a look at how much memory we can save. So with n equal 5,000. Okay. If you type in who's A, it gives you the size of A, this many bytes. Okay? This is 10, 24 divided by 10, 24. $190 megabytes just to store this matrix of 5,000 by 5,000. Okay. Now, if we do the same thing with sparse A, let's see. So you go here. All right, sparse A has 5,000 by 5,000, and let's say who's sparse A. All right, that many. Let's see, how many is that? 714 times less memory. It's a huge, huge amount. Okay. Instead of 200 megabytes, now we are using 0.26 megabytes. All right. Again, we have not done anything special. Just one line helps us save almost 1,000 times in memory. Okay, and these simple solvers that are already coded in for you help you save 20 times in computation time. So it's very, very useful to know these things. All right, let's time them. Right, fine. Let's let it run. Oh, it's already done. Okay, so full time took a full inverse took 5.3 seconds. With a sparse matrix, a full inverse takes 0.5 seconds. Sparse iterative solve takes 0.1 seconds. A full iterative solve takes 0.23 seconds. Okay, so very useful. No matter whether you do CFD, you do finance, okay, you can impress your bosses a lot just by doing these things. Questions? My advice is use these things as much as you can for your homework and projects. That way you will get very familiar with these. Okay? No questions? All right, one more loose end we have to tie up is boundary conditions. We've talked about mainly about boundaries where our temperature is given, right? There it was given 100 degrees C on the left, 20 degrees C on the right. But what if it's some other physical problem? What if we have a Dirichlet on one side and a Neumann on the other? What I mean by that is, so boundary conditions. So again, we take our log, we say on the left side, we fold it at 100 degrees centigrade, and on the right side, we set del t del x equals 0. Do you remember what this is called? So what this type of boundary condition is called?
The left one is Dirichlet and the right one is Neumann.
Yeah, this is called Dirichlet boundary condition. And the one on the right is called Neumann boundary condition. Okay? We know how to deal with this one, the one on the left. So I equal 1, 2, 3, 4, 5, blah, 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 right? So we know we don't need to solve for t1 at any n, or t1 basically, n plus 1. Since it is held fixed at 100 degrees centigrade. Okay? For I equal 2, we know, let me write this out quickly, t2 n plus 1 minus t2 n over delta t. A fully explicit solve would get t3 n minus 2, t2 n plus 100, right? Delta x squared. This is basically t1, right? And everything is known, all the n level t's are known, the only thing unknown is the n plus 1. Okay? What happens at before we do that, what will happen physically? This is a metal rod. I'm holding one end at 100 degrees centigrade and the other one has dt by dx equals 0. What will happen to the rod? The rod will disintegrate in a flame of fire. What? No, it won't. My question is, what will happen to the rod physically with these boundaries?
One of them is constant temperature, the other one is conduction.
Exactly. Maybe I forgot to mention dt by dx equals 0 implies it's perfectly insulated, right? Just in case somebody doesn't know. So if we have a metallic rod, one end, as you were saying, is held constant at 100 degrees centigrade. You have a flame there, you keep adjusting it. Anytime it tries to change, you either lower the flame or increase the flame, so the temperature remains at 100 degrees centigrade. The other side is completely insulated. So what will happen to the, if you start with 0 degrees centigrade everywhere, you take it out to the freezer and start doing this.
The whole world's going to be
Temperatures.
100 degrees.
All right, what was that?
It's going to come to an equilibrium.
It's going to come to an equilibrium immediately.
No.
All right, what will happen?
It'll slowly heat from the left end to the right.
Yeah, exactly.
Right side meets the same temperature.
So everything was at 0, suddenly I make this 100. Slowly, this, so that's like an infinite jump. Slowly this will diffuse out through the rod. And everything will start increasing from 0 up until everything reaches 100. And when everything is 100 degrees centigrade, there's no more gradient left. So it will be the steady state. There's no spatial gradient left. It's a constant at 100. So that's what will happen physically with these boundary conditions. If instead you hold the other end at 0, do you know what will happen? Instead of having this Neumann condition, you have Dirichlet on both sides. 100 here, 0 there. What will happen? Initial condition is 0 everywhere.
There will be a linear gradient.
Maximum in the middle.
Maximum in the middle, why do you say that? So it's 100 here, 0 there, right? Everything else is also 0, initially. So you're saying it's 100 over here and it might be a 200 in the middle?
No, minimums.
Yeah, it'll be a linear gradient.
Yeah, it will be a linear profile for you. 100 here, 0 here, and everything in between is perfectly linear. And this is one of the first things we actually looked at a long time ago. The steady state solution has the curvature is 0, right? So the profile has to be linear. And if you hold one side to 0, other to 100, it will be a straight line between the two. Okay. All right, so that's what, and physically that's actually what happens. Okay. So let's come back to our boundary conditions. We know how to implement our Dirichlet boundary condition. We just put it in the equations wherever we need to. What about the Neumann boundary condition? So if I write for I equal 8, what will I have? T8 n plus 1 minus T8 at n over delta T equal what? All right, equal
9.
once more.
9.
Did you say I?
No,
9, yes. 9 n minus
2T8 then.
plus
2, 7.
T7.
perfect. So this is known, this is known, this is known. What happens to this one? Now we don't have a given value of T9. There's no given boundary value. Instead there's a dt by dx. What do we do?
We can assume that T9 equal to T8.
Right. Why would you assume that?
Because dt by dx equal to 0, and so T9 minus T8 equal to 0.
Exactly. So that's our given boundary condition, right? That's exactly what we mentioned. So let's see. For I equal 9, we are given that del t by del x at I equal 9 is 0. Okay? And one discretization for del t by del x is T9 minus T8 over delta x equals 0, okay, which gives us T9 equal to 8. Make sense? So yeah, now we can substitute this T9n with T8n. We have used the boundary condition to get to that. Is this the only assumption? Is this the only way to find out what Tn might be? Are you happy with me using a first order derivative approximation? Do you know what I mean? No. Okay. So I just use the finite difference, right? It's a, where is my, all right. It's a Ti minus Ti minus 1 divided by delta x, which is one approximation of a derivative, one-sided finite difference. You might say, no, that's a crappy approximation. What else could you try? Okay, in case it's still a bit confusing, so here we have used the approximation del t at del x, del t by del x at I is equal to ti minus 1 over del x, right? You remember that? We did that with finite differences. Okay. Is there something else you can try?
We have to assume for something after that, and then right central.
Yeah, that's a very good point.
Like goes down.
We don't know what T10 would be because it's outside our rod. So your point is we can assume something and then write a center difference. Okay? But what would you assume?
The boundary is 0, so the Newman condition.
It's difficult to assume something, right? But what we can do is we already used a one-sided difference of first order. We can do a one-sided difference of second order, right? Meaning we can write that instead of this first order of approximation, we write it as, I have to check, 3t minus t, okay, so it's 3 times ti minus 2 times ti minus 1 plus ti minus 2 over 2 delta x. Make sense? Yeah, so we could have used a higher order one-sided difference. Okay, and then we would get something different. So we would get 3t9 minus 2t8 plus t7 over 2 delta x equals 0, which implies t9 is 2t8 minus t7 over 2. Again, the T8 and T7 values are known, so now I know my T9, which I can go back and plug in over there. So that's how you deal with Neumann boundary condition. All right. Now there's one more very interesting and very simple seeming boundary condition called the periodic boundary condition. Okay. Then we switch to the animation again. I will wait for 1 minute while you finish. All right. Okay, periodic boundary condition. What is that? So, what's happening in this animation?
Basically, whatever happens on the right, that side happens on us.
Yeah, exactly. Anything that happens at the right boundary happens at the left boundary. So that's exactly what a periodic boundary condition is. So if you notice, this peak moves to that side. So if I manage to stop this, all right, perfect. If I want to compute a derivative over here, what can I do? Do I have to do this one-sided difference? It's the same problem, right? If this was node number 9, there's no node number 10. So either I go one-sided, or what can I do? If I tell you this is a periodic boundary,
Then you're repeating the
first node.
the first node from over here.
Yeah.
Yeah. So you would say I have a node number 10 whose value is exactly equal to node number 1. Okay? So that's how you implement a periodic boundary. Conceptually, it's very simple, but it's a little bit tricky to implement. And you will see this when you do the second project. But it all makes sense once you do it for one time. So how would you do it? Let's see. If we have so again, if you have 1, 2, 3, 4, 5, 6, 7, 8, 9. And we are told that the boundaries are periodic. Okay? The way you implement this numerically is you have extra cells over here. Okay? So I will use another color. Let me call this 10, let me call this 11, let me call this 0. 0, no, let's call this -1 and -2. Okay? And these are called ghost cells. Ghost cells. Alright, so one possibility is every time I come here, I ask my matrix what its first element is and then use that in the computation. A simpler alternative is every step you basically copy these values into these cells, these values into that cell, those cells. So what that means is this is fancy. Okay, let's see how to measure this. These values get copied to here. And these values get copied here. Make sense? Sorry. So that's exactly what we were saying, right? If we are at node 9, the one on the right side will be equal to 1. So we just copy back 1 to 10. And what about number 11?
Equals node 2.
Number 2.
Yeah, number 11 should get what number 2 has. Okay? So you copy that chunk over there, and the same on the other side. You copy 8 and 9 to -2 and -1. All right. So why is this necessary? Why not? I mean, it's a simple thing, right? I can just say, give me my matrix 1 or vector element 1. This is very useful if you're doing, for instance, advection. You remember? That's exactly what I showed you right now. So del phi by del t plus u del phi by del x equals 0, right? We used a concept called upwinding. So if I'm at 9, if I'm at I equal 9, let's say, so if we are at I equal 9 and u of I equal 9 is positive, let's say +1 meter per second. what would your derivative be in that case for del phi by del x? Would you bias right or bias left?
It's T10 minus T9.
Why?
This direction is,
Okay.
is forward.
So information is moving in this direction, which means information came from the left, right? Okay, so the question is basically this. For I equal line, I give you u is positive, what is d phi by dx?
T9 minus.
So you're saying it would be phi 9 minus phi 10, because you're saying the information here moves to the right, but that means the information I'm interested in came from the information at 9 arrived from
From 8.
from 8. So we should bias our stencil that side. Okay, make sense? That's it. That's what we were talking about for upwing. So when the u is positive, our d phi by dx would be phi 9 minus phi 8 over delta x. If ui equal 9 is minus 1 meter per second, then it's what you just said. Right? Then d phi by dx at I equal 9 would be phi 10 minus phi 9 over delta x. Is this confusing? No. All right. So yeah, sometimes it messes me up too. If u is negative, meaning information is moving to the left side, so I should take the node where information came from. Okay. Yeah. So with advection, depending on what the sign of u is here, you would have to take either the left or the right. And it becomes very cumbersome if you write that in code. You have to have many if statements. So the alternative is, after every time step, just do this correct copying data into the host cells. And then it's there for the computation to use. There's no go fetch from there. Okay. This also has this is the heart of parallel computing. So I'm going to run out of time, so I will tell you the next time how ghost cells are used in parallel computing. Okay, so to implement periodic boundaries, we copy appropriate data into the ghost cells every time step. And again, you will have to do these things for the project. So, okay. So, any questions? We have less than 1 minute. All right. Again, the project is due Thursday, midnight. Please, if you have any questions, bring them in class. Bring them to class on Thursday. And Thursday we will finish up with some final numerics and move on to Navier stores. Okay. So I'll see you then.